Welcome DC Circuit students. This is the third video in our series in constructing and measuring a parallel combination of resistors and a single voltage source. So we are back to our measurement circuit, and I'll be moving the camera several times to highlight different parts of the circuit. So I'll just use my pen to show. We have our three resistors in parallel, our nominal 2700, 2200, and 3900 ohms, which we've measured exact values for with the multimeter previously, and we have these hooked with our power rail to our 9-volt battery source. So new addition since video number 1, and I'll go ahead and take the clips off. I've added 2 measurement leads. So I've just taken a piece of wire, stripped the ends, and now I can use this as a measurement point in my protoboard. So plugging that in there, I am now measuring I'm giving myself an easy clip-on measurement point for anything that is continuous on this next to this blue strip on the protoboard. And as it turns out, if I trace my leads back, I find that that is connected to the red wire on my battery connector, and the red wire by default means it's connected to the positive of the battery. So if I want a positive voltage to read positive on my meter, I'm going to use my positive meter connection for that. And I've done the same thing with the other power rails. So now what I can do is I now have the circuit energized. I've completed the circuit, and so if I look at my meter, I can see what is the actual circuit voltage with current flowing. And as it turns out, we have a very well charged battery. It isn't depleted at all, and I'm actually getting 9.15 volts DC. So I'm going to go ahead and I'm going to disengage circuit. So that's my actual source voltage. So all of my as calculated currents from the previous video would need to be ratioed up in a ratio of 9.15 to 9. So I'm just going to note down that that's my actual source voltage with under load. So it's a little bit more than I expected. Sometimes batteries have an open circuit voltage that's significantly above nominal. So in this case, because our total resistance actually is reasonably high, we're actually seeing something above nominal, which is not unusual. Okay, so my next objective is going to be to confirm the source current, the I source. So for that, first thing I'm going to do is I'm going to get rid of a few extra wires, and I'm going to remove the measurement points that would tempt me to put my meter into parallel with the circuit. I am going to change my connection to current measurement. So I'm now measuring between the common through a fuse and through this point. So I'm going to remember to have to put my meter in series, not in parallel, or I will blow that fuse, which is certainly better than ruining my meter. The nice thing about having pre-calculated is I can use the more sensitive range, because I know my total source current is going to be somewhat less than 10 milliamps, so I'm definitely safe to use the 40 milliamp or 400 milliamp range. So this will give me a lot more accuracy. My plus or minus is going to be much less, because you can see basically my lowest measured amount is somewhere around 0.05, 0.06 milliamps. So that would be what's known as the counts when you're looking at your meter plus or minus accuracy. It's going to be a certain percentage according to the meter spec of your as measured value plus so many counts, and that count is based on the lowest reading on whatever scale you're using. And so we will address that after we make our measurements. So I'm going to be very careful. I'm going to put my, again, put my meter in series. And so basically I'm going to trace back. We have the positive current flowing through my circuit, coming out here. So I'm going to have it flow through my meter. So I'm going to have what's effectively positive coming out of the circuit, flowing into the meter, through the meter, out of the meter, into the negative terminal of the battery, which I'm connecting with an alligator clip. So now my meter is in series, and as you can see, the first thing I'm noticing is, oh my goodness, this measurement is fluctuating all over the place. Well, it is because it's trying to get an average, and it's because I have the meter set for AC, not DC. So I'm going to reconfigure it by pushing that button. So now you can see it's measuring DC, and it's 10.04, which is very close to our pre-calculated value of, I think, something like 9.18. We have a slightly higher source than we thought we did. So this is definitely within expectation. So I'm going to write that down. I source as measured is 10.03 milliamps. Now, just to keep the current from flowing and depleting my battery, I'm going to break the circuit. Having broken the circuit, of course, I can see my current's going down to some error value. Now I might want to verify my calculations of the circuit, of the current through each branch of the circuit. And in that case, I'm going to have to, trying to zoom in on now on this part of the circuit a little bit better. So now I'm going to want to break the circuit at each one of these resistors and put the meter in series with that resistor. Okay, so there's probably a lot of different ways to do that that would be more or less elegant. But one of the ways to do that is to just go back to the thinking about giving ourselves a measurement point that we can connect, and it is very bad practice to do that through the component, but in this case that might actually be the easiest thing to do. So I have now given myself, I've taken out the resistor and I have put in a measurement point, and so now I'm going to connect my ohm meter through this resistor. And I can't remember honestly which resistor that was, and as I can't see the color codes, I'm going to reconfigure my meter very quickly and confirm which resistor I'm using. I've reconfigured to ohms. This is the nominal 2700, so I'm going to make sure to reconfigure back to ammeter. So current is going to flow from my battery, positive, into this left-hand side of the circuit. So I'm going to want to make it flow through my meter, positive to negative, and I'm going to connect that resistor branch through the meter. And now I'm going to energize my circuit. So I don't let myself have any way of connecting the meter in parallel. I force it to be in series. And I go back to milliamps. It defaults to AC. So if you can see the reading, 3.43. Just going to write that down. 3.43 milliamps for the 2.K resistor branch. Okay, I'm going to break my circuit with the battery. I'm going to then repeat what I just did, disconnecting each resistor connecting the meter positive to negative, forcing that current to flow through the meter in series, and then energizing the circuit again. So now I'm going through the larger resistor, the nominal 3900, and I have 2.36. I think we're beginning to see the battery coming down just a little bit. That's through the 3.9K. So I disconnect my power source. Each time I make and break a connection, I'm turning off the power. That way I don't have wild fluctuations going through my measurement instruments, which is not a big deal with a multimeter, but when you start working with a little bit more reactive and fussy instruments like your USB oscilloscope and later on more sophisticated instruments maybe on the job, that will save wear and tear on the instrument and possibly avoid some erroneous problems or even damage to the instrument. So I'm going to my last resistor. I'm going to use my measurement plug, my measurement point wire. Okay, so now I am ready to measure resistance. My meter is in series with my final resistor, that one on the end, which is now kind of in a vertical position. And I connect my battery, and I get 4.29 milliamps, and that's going through the 2.2K nominal resistor. Okay, maybe 2.85. Okay, I'm done. I've disconnected my battery source. I'm reconfiguring my meter to voltage measurement. Now this is the safer way to configure it, so if I inadvertently put it in parallel and make a measurement, that it's not going to blow the fuse. And in most cases I'll be doing voltage measurements in the future. I'm going to reconnect my resistor. So now one of the first things I can do is I'm going to go back and look at my data, and I'm going to pull up the specifications for my multimeter and step through some calculations to tell myself how much of these current measurements I can really believe based on how accurate my meter is. And then I'm going to step back and adjust my calculations for my 9.15 volt source and just see how all of the numbers compare. So I'm going to pause this video, and when I pick up again, I'm going to start by stepping through the specifications on my meter and walk through how we put error bars around our measurements. And then we'll go back and use an Excel spreadsheet and do some on-the-fly checking of our calculations and adjustment for that higher source voltage. Okay, welcome back to our parallel circuit measurements. Now we are looking at our digital multimeter specifications. I happen to use a Fluke 177 meter, and these are the electrical specifications. So you can see that that's down kind of near the bottom of the specs, and we can look at basically what is the plus or minus, see accuracy plus or minus range that we can assign to our actual taken measurements based on what the actual current range is and then what the resolution was, the lowest possible reading for that range. So basically the rule of thumb is the larger the range you're measuring, the less accurately you can measure it. So lucky for us, we were measuring on the most accurate range. And I'm going to get a little pencil here. So we were measuring in the 60, I can't use a pencil, but we were measuring here in the 60 milliamp full scale range. So that means our resolution was 0.01 milliamp. So for that range, our plus or minus is going to be 1% of the reading we took plus 3 counts, and a count is a 0.01 milliamp. So for our first measurement that we measured an eye source of 10.03 milliamps. So we can grab our handy dandy calculator. 0.76. So we would say 10.03 milliamps. 1% of that we'll multiply by 0.01, and we get 0.1003 milliamps. And we'll add to that, whoops, bumped to the other page, or amps, plus 3 times the lowest reading on that scale, which is 0.01. So we have 0.1003 milliamps plus 3 times 0.01. That equals 0.1303. We'll take the first 2. So I'm going to scribble on the bottom margin. We measured an eye source. I'm using my Wondershare to just write right on this back here. I don't have to save it. So we had a measured value of 10.03 milliamps. A little bit messy here. So we're going to do plus or minus. So this is kind of the error bar. 1% of the reading, so 1% of 10.03. We just kind of move the decimal point over a couple of places. So we have 0.1003 milliamps. All this is in milliamps. We can't forget that. Plus 3 times our resolution, so 3 times this, plus 0.03 milliamps. So we have 10.03 milliamps plus or minus, and we're going to lop off everything below the second decimal place because that's as far as we can actually state anything. Plus or minus 0.13. So if we take a look at that, we have 10.03. We could be minus 0.13, so we could be as low as 9.9 milliamps, or as high as 10.03 plus 10.16. And the meter couldn't tell the difference. We can be anywhere in that range. That's a 6. It's kind of hard to draw without my tablet. So what it says is for any value between those, the meter's blind to it. Our nominal number, our nominal measurement is 10.03 milliamps, but the real value of that source current that was flowing when we made the measurement could have been as low as 9.9, or it could have been as high as 9.90. It could have been as high as 10.16. So when you make a measurement, if you are asked to provide the error of the measurement, or you have a lower or upper threshold that you can't exceed, always make sure to look at the accuracy of your meter and add in or subtract, depending on what your critical value is that you can't exceed or you have to be above. Make sure that you're still okay when you add the error of the meter. So in this case, we were very lucky that we have very low error, but if you look at it proportionately, it is give or take. We didn't add much with the counts. With 10.03, we have an error of 0.1, so it's about 1%. If you look at what other meters have, they don't fare quite as well. The 1.5, they're all the same in this range. Some other meters, much lower range meters, might have an accuracy that is less favorable, or they may not have a setting that measures quite this low. So we can go back and apply that same calculation to our I1, I2, and I3 and figure out what the plus or minus actual value is for each one of those. So if we go back and we compare to our calculations, let me take a quick pause here and bring those up. Okay, we're once again looking at our preliminary calculations. So for our lowest resistance branch, you can see we had predicted about 4.19. We measured 4.29. And in our highest resistance branch, I3, we measured 2.31 milliamps. We measured 2.36, and in our middle of the road, nominal 2700 ohm, we measured 3.43, and we predicted 3.35 milliamps. So overall, our nominal, not counting meter inaccuracy, meter accuracy range or plus minus, our as measured values were generally all a little bit higher than our predicted. So last thing we're going to do is, and I'll be pausing the recording again to pull up a spreadsheet, we're going to walk through an easy way to ratio or adjust all of our measurements for a different source voltage than we thought that we were really getting. And that's very useful for cases where you're imposing an AC signal later on when you're doing periodic voltage or current delivery, where you have what's known as a sagging source or a low current capability source, which will give you whatever voltage it is able to based on the current it can supply. Many function generators, especially a USB type function generator like the one that is on the Picoscope, is very, very current limited. So quite often if you have a circuit with a low resistance or a low impedance for the frequency, the function generator that is acting as a voltage source simply can't supply all the current you need, and so it will operate with a much lower than you thought it was supply voltage. So adjusting all of our predicted currents for the real as opposed to the nominal or expected source voltage or circuit voltage is very good practice for what you'll run into later. So I'm going to pause this recording and I'm going to pull up a spreadsheet and populate it and show you how to walk through an easy way to make that adjustment. Okay, here we are back in our Excel spreadsheet, or we've opened an Excel spreadsheet, and I've added a little bit of formatting, and so I'm going to walk through how you use a spreadsheet to do some calculations where you can adjust something. For those of you who are not familiar with Excel, I'm not going to include a complete tutorial in Excel, so I can refer you to some excellent tutorials in the CAP 101 class if you're at Bellingham Tech or on YouTube. Try to include some of those, but I'm just going to show you how we can use it for this electronics parallel circuit calc. So just general good practice, always label your spreadsheet. So here we have parallel circuit branch current calculator. I like to use a default cell entry versus calculated cell color scheme. So anytime I have a yellow highlight in my spreadsheets, those tend to be data entry values or user entered. These are not calculating cells. They're things that you would enter that are specific to your circuit or your problem, and then I use a green highlighting for a cell that will include a formula that operates on the yellow cells and maybe whatever constants. So I'm going to start by putting in a formula here for REQ. That is our parallel circuit formula. So to do that, I click on the cell and then I come up to the formula bar and I always hit equal. That's how you tell Excel that you're going to enter a formula. So I'm going to have a parentheses, and then I'm going to have, I'm going to enter my first resistor, raise it to the -1. Oops, yes, it didn't like that. It doesn't like a tab or a space when you're entering a formula. I'd forgotten that. So then I'm going to add the next resistor. I'm going to raise it to the -1. I'm going to add the last resistor, and when I add those values, what I'm adding is the cell position where I will add a value. Since a spreadsheet acts on positions or places where you're going to put something rather than the value itself. So the cell is like a variable, so you can put anything you want in it. And I'm going to raise the whole kit and caboodle to the -1, so the up caret is the exponent. So I have a set of parentheses, and then I have whatever I'm going to put in cell B5, which is highlighted in blue here. I'm going to raise it to the -1. I have whatever I'm going to put in cell B6, raise it to the -1. I'm going to have, and then I'm going to add to that whatever I'm going to put in cell B7, raised to the -1. I have the whole thing in parentheses, and I'm going to raise the whole thing to the -1. And not surprisingly, I have a divide by 0 error because I don't have anything in those cells yet. So let's go ahead and put our resistor values. So I'm going to just go from low to high. I had 2150 ohms, and then I had 2686, and I had 3893. So now we have, surprise, surprise, our previously calculated REQ that popped up. So given that that matches reasonably well, that is a little check on my calculations. Now if I want to calculate the source voltage, what I can, or excuse me, the source current, so the current flowing out of the battery that will then branch and divide and go through each of the resistors, I can use this REQ and whatever I end up having, what I decide my source voltage was. So I can highlight where I want to put this formula, and I go up to my formula bar, I hit equals, and I like to put things in parentheses just to make it a little easier. So I'm going to apply Ohm's law. So I'm going to say the source current is the source voltage. Well, I plan to put the source voltage up here in cell C3, and when I click on it, look at the Excel goes, aha, you probably want to do something with cell C3. And I'm going to divide by REQ, and to fetch that number, I highlight the cell it's in. So voltage divided by resistance equals current. There I go. And so 0 current. Well, good heavens. How do I have no current? I measured 10 milliamps. Well, it's because I haven't put anything in for a source voltage. So if I put in 9 volts, I get, and now this is in amps, not milliamps, so I would have to multiply by 1,000 to get milliamps, but I can just mentally move that decimal place over 1, 2, 3, and get 9.849, which is pretty close to what we had calculated originally. But we measured 10.03. But we also measured our source voltage operating the circuit, even with current going, was actually 9.15. So if we put in the actual source voltage, now we're getting 10.01, which is very, very close to our 10.03 that we had measured. Definitely within the error of our meter accuracy. So that's a good thing. So that says that when we adjust for our real source voltage, we actually got something very, very close to our measurement and within the capabilities of our meter. So that's a good verification. We can go ahead and do the same thing applying Ohm's law individually to the resistance of each branch and calculate each of the branch currents and do that same comparison. So I'll do the same thing for current through the nominal 22.2K or 2,150 ohm resistor R1. So we go equals source voltage, I won't use parentheses this time, divided by resistance 1, gives me current 1. So I have about 4.25 or 4.3 milliamps. I had measured 4.29, so again we're a little bit on the low side, but within our meter error. I can just keep going. I2, 3.4. We had measured 3.43, so this would be 3.41 if we were to round off to 2 decimal places on a milliamp scale. And then last but not least, I have what should be my lowest current going through that big resistor. Current flows through all paths, but it flows through the path of least resistance preferentially. So 2.35, and we had measured 2.36. So remembering that we have about a 1% error with our measurements, these are very, very close and well within the meter accuracy. So, but definitely looking closer when we adjust for our source voltage. Now, the nice thing about putting this in a spreadsheet this way is, what if the battery started to exhaust? What if we did a whole lot of measurements and maybe we had a very low resistance circuit and we left the battery connected while we went to lunch and we came back and went, oh my goodness, I left my circuit energized when I stepped away from it. Very bad practice. And maybe our source voltage dropped to something like 8.0 volts, depleting the battery. But we had to make a couple more measurements. And we wanted to, of this circuit, maybe with a different resistance value in one place or another. Look how all of those changed automatically. We didn't see a change here because this formula does not include the source voltage. This is just our parallel resistor combination. But every one of these formulas does include the source voltage. So you can click on a cell and then click on the formula bar, and it will highlight each cell that it draws from and then color code it to the variable in the formula that it corresponds to. So we could instantly ratio everything if we already had something set up and we had to compare maybe our before the battery depleted to after the battery depleted values and compare those really easily without having to go back through a bunch of hand calcs. So this is an example of how just simply automating the calculations we already know how to make on paper, but automating them in a spreadsheet so they can be repeated with different input variables can be very, very useful and allow us to make comparisons quickly with less chance of a calculation error between. So this concludes our little mini lab exercise in parallel circuits. So just to recap, we started by basically building our circuit. We presumably would have been given the 3 resistors that we had. I personally did some calculations in advance and made sure that they wouldn't exceed the power capabilities, but maybe we were checking for a friend, maybe on the job. Your boss or another colleague might hand you a circuit and say, hey, could you build this with these components? We built them with our proto board. We put them in parallel and we gave ourselves some good connections and measurement points to be able to connect our battery. We verified continuity, and at the same time we got an initial measurement with our multimeter of our equivalent resistance of the 3 resistors. Then we went to our calculation sheet. We calculated equivalent resistance. We confirmed that we would not be exceeding the power capabilities of each of our quarter-watt resistors, and we applied Ohm's law to calculate total circuit current and current through each branch. Then we came back to our proto board. We measured everything we calculated. We also measured the actual source voltage under load. Then we went back to our meter specs and we put error bars effectively around each of our measurements. Turned out that they were very small, which was nice. And last but not least, we input our as measured values into an Excel spreadsheet, and we adjusted our predicted source voltage and currents for our actual source voltage, and found that our predicted currents measured matched our as measured currents very well, and well within the error bar accuracy range of our Fluke 177. This is the type of sequence that you can follow with every one of your labs, or every exercise you may have to do, assignment on the job. Always start. In fact, if you were on the job, you would want to start with the calculations before you maybe even built that circuit. You'd want to confirm that it was safe in terms of power dissipation, and get an idea of what your total equivalent resistance, your total currents would be, and that will help you. Maybe you might have to go back to your boss or your colleague and say, hey, I think we need to use a bigger resistor, and we're going to toast something. Much easier than after you have it built. Get an idea of what your expected measurement values are. Make sure you have your meter or your other measurement instrument connected properly. Does it need to be in parallel? Does it need to be in series? You may need to make sure that you don't have too much current flowing through a measurement instrument. Many of them are very, very sensitive. Make your measurements properly, and then assign error bars appropriately, knowing the resolution of your instrument. Multimeters tend to follow the percent and counts. Other measurement instruments will have different resolution accuracy demarcations. You'll have to follow the manual. In either case, always put error bars around your measurement. Noting, in this case, we measured our resistance of each of our resistors ahead of time. If you're using nominal values, you would want to include that in your total as measured error. So rounded them all up and compared, and now we would be ready to include all of this in a report of how our parallel circuit was expected to behave, and in fact did behave. So that is it for this video series, and please stay tuned for other ones in the modules that go with your course.